Okay, class, let's do this. Okay. Take your time. Copy down the details are in, how they're important. So every little thing, I'm going to take it nice and slow. I'm going to try and get 2 problems done this period. I know in the next half hour. So I'm going to take these right out of the textbook. If you want to go back and read them, you can. Okay. And you do have a couple of them to do tonight. Nice. The ones I'm doing, number 77. This is the first problem I'm going to solve. It's a little bit shorter because it's a mole problem, one-step problem once we get to the stoichiometry problem. Now realize that when we talk about limiting reactions, just like your nuts and the bolts that we just talked about, one of them is going to run out, one of them is going to have extra of it. So you'll notice when we write these problems out, number 77 says, in 1901, Thomas Edison invented the nickel-iron battery. The following reaction takes place. And it's pretty interesting. Okay? Iron reacts with nickel something or other. Please don't ask me what this is. I have no idea. Nickel oxide hydroxide. I don't know, it's really weird. And it forms these 2 products. Iron 2 hydroxide. And the second product is nickel 2 hydroxide. They give us a couple coefficients here. Oh, and there's some water in there too. Stick that over here. It's not really important except for balancing purposes. And so the coefficients that they give us are 2 and 2. Now just a quick hint. If the book gives you a 1 or more coefficients, it might be balanced. It's always a good idea to double check. We checked this one this morning. It is balanced the way the book says, but always double check. If you're looking at a reaction on a test, on a quiz, in the book, on a website, always double check. You just can't tell. I've found enough errors in people's balancing that I always double check. Now, the rest of the problem says, how many moles of FeOH2 is produced? Okay, that sounds normal. We've been doing stuff like that all week. If 5 moles of iron reacts with 8 moles of this stuff. And it says 8.00 and 5.00. Let's see. Now, what's different is something should automatically jump out and say, oh, that's different than everything we've done this week. What's different about this one? Connor? They give us 2 starting numbers. They're still only asking us 1 answer, but I have 2 things to start with. Every problem we've done in stoichiometry so far has only had 1 starting place, and so I knew where to start. So when you see 2 starting places, it's a limiting reactant problem. We need to figure out which one of these is going to control or limit that reaction. In some of your groups, the nuts ran out first and you had extra bolts. In a couple of the groups, the bolts ran out and you had extra nuts. Okay? So, in this case, I have no idea. I'm going to show you how to figure it out, but I have no idea just by looking at it. I had nobody on the planet. I don't. Maybe there's somebody, but I don't know anybody that can just look at that and do it in there. Okay? You got to do the steps. You got to take it 1 step at a time. So the question is this going to run out and this will be extra, or is this going to run out and this will be extra? Okay? It all comes down to ratios, mole ratios. So step number 1, I'm going to make 2 columns here. I'm going to put a what I have. Sometimes I call this the given column. What am I given in the problem? And what do I need? Sometimes this is called the theoretical, or what is the ideal ratio. Okay? How much of these do I have? How much of these do I need to make this reaction go? So I'm going to compare 2 sets of numbers here. The first thing is I'm going to take a ratio. Now this has to be a mole ratio. I'll show you in the next problem, if we start with grams, what you have to do first. But this is already in moles. So I can take 5 moles and 8 moles, and I just put them into a ratio. I can put this over this, or I can put this over this. To me, I don't like numbers smaller than 1, so I always put the big number over the small number. But you don't have to do it that way. I'll show you in a minute what happens if you do it backwards. So we're going to take 8 moles of nickel stuff, and I'm just going to call it Ni ... okay, because I don't want to write that whole formula out 1,000 times, and divide by 5 moles of Fe. Over here, the ideal ratio of that nickel stuff to iron would be according to the coefficients, 2 to 1. So write out the same thing, follow your same units. Now they have to be in the same order. Whatever you put in the numerator here has to be in the numerator over here. 2 moles of nickel stuff, ... divided by 1 mole of iron. Okay, everybody with me so far? Now, the next step is I cannot compare 2 ratios or 2 fractions unless they have the identical denominator, right? I don't know which one of these is bigger, I mean, these are simple numbers, you can figure it out. But what I always do is divide them. So I will literally take my calculator if I need to, 8 divided by 5. Now, 8 divided by 5 is 1.6. I know that, I can write it down, but if you need your calculator, 8 divided by 5 is 1.6 over 1. And I always put that denominator in the denominator, the 1. Over here, doesn't change. 2 divided by 1 is what? 2. Okay? So this 6 okay, once you get these 2 ratios and both the denominators are 1, we need to do this, okay? This is where you need to stop and think. This is challenging. It's challenging to think. Most of you are so smart, you just want to know how to do it, get it done without using your brain, okay? You actually have to use your brain in these problems, okay? It's called logic. Ready? This is what I have. I have 1.6 moles of nickel stuff for every one of these. This is what I need. I need 2 moles of nickel stuff for every 1 mole of iron. Is the nickel stuff going to run out, or do I have too much nickel stuff? Okay, I'm literally comparing these 2 numerators now. If this number is smaller than what I need, it's going to run out, right? It will be the limiting reactant. If this number happened to be bigger than that number, it would be the excess, and the other one would be the limiting reactant. So let me stop here for a second. If this is small x, I need to have 2. I only got 1.6. I'm going to run out. So the limiting reactant is the nickel stuff. I'm going to go back to the beginning of the problem, and then before I do anything else, I need to make sure I know this is my LR. And that's my abbreviation. That's not a textbook abbreviation. But you'll see me use it. You're welcome to use it. You don't have to. Limiting reactant is LR. Now, any other reactant, and we're ignoring water in this thing because it doesn't even mention it, okay? The other reactant is going to be the other one, what we call XS. And I abbreviate that as XS. Okay? You don't have to use that. You can write EXCESS if you want. But I don't like writing out long words if I can abbreviate things. So, I know which one I need to use now. The limiting reactant is the one that's going to control the reaction. This one, I'm going to have plenty of. There's going to be some left over when I'm done. So I'm going to ignore it. Put an X through the number that you will not use. The excess one you will not use because you don't need to know it. It's got too much. It's got more than you actually need. More than the stoichiometric relationship shows. Okay? So once I determine what is the limiting reactant, nickel stuff. And then I'm going to use this number now to do the problem, because we haven't started the problem yet. Okay, now we're going to do the stoichiometry problem with 8 moles of nickel stuff. So now we start the same as we've been doing all week long. 8 moles of nickel stuff, 8.00 moles of NiOOH. For some reason it's in parentheses and there's only one of them, which is weird, but that's okay. And what are we going to multiply? This is in moles. What's it asking for? Moles. So I go to my flow chart. My flow chart says I'm starting at step 2. I'm ending at step 3. One-step process. I need a mole ratio here. Moles of nickel stuff to moles of NiOH2 or something like that. Is it iron hydroxide we're looking for or nickel hydroxide? Iron hydroxide. Okay, you'll look at your balanced chemical reaction, and my coefficients are what? Iron hydroxide is what? The 1. Nickel OOH 2. Okay, so that's my mole ratio right here. That's my mole ratio, step 2 to step 3. And then I put my equal sign, check my units, do the math. 8 divided by 4. What? What did you say? Oh. Yeah, you're right. I said 8 divided by 4. You said 4. But 8 divided by 2 is 4. Okay? Put your 3 sig figs there so we can match the number that was given in the original problem, and we have our answer. 4.00 moles of FeOH2 are produced. Box around it, and we got it. Okay, so a limiting reactant problem. Number 1. Figure out which one's the limiting reactant. And sometimes that's more work than the stoich. Okay? Step number 2, once you know the limiting reactant, use that number to do the stoichiometry problem. Bear with me? Okay. Now, I'm going to show you. How about if I flip this upside down? Mr. Debski, how about if I got these upside down? Will I still get the same answer? Watch it out. Suppose instead of 8 over 5, you put 5 over 8. 5 moles of Fe over 8 moles of nickel stuff. And over here, that's going to be also upside down as well. 1 mole of iron over 2 moles of nickel stuff. Okay? So 5 divided by 8 is 5/8, 0.625. And 1 divided by 2 is 0.5, right? Decimal over 1. So now we ask ourselves the same question. This is what I have, 0.625. This is what I need. Do I have enough? Do I have more than enough? You say, well, you got a different answer. No, because look, now I'm talking about iron. This tells me I got more iron than I need. So it's excess. Say, isn't that different? No. Iron was the excess. And the other one is now going to be the limiting reactant. So don't worry about which one you put in the numerator, as long as you're consistent in your work and you keep the same numerator in each and the same denominator in each. You can do it both ways. One will show you the excess, and the other one will show you the LR, limiting reactant. And the other one always has to be the other one. Okay? There's always going to be one LR and one excess. One limiting reactant and one excess, at least in this class. Next problem. The next one I'm going to do starts in grams, finishes in grams. It is number 81, if you want to follow along again at some point in the future, on page 394. 91 says, no it doesn't, 81. Alkaline battery, more battery problems. Hey, on your research papers, guys, good job. I went through the list last night. I got my master list compiled. I got the whole check off. If you didn't sign up for one, Ben, you need handouts, right? Hand this over to him. Who else just got back? Taylor, did you ever get research paper? Flow chart? Research paper, flow chart, did you get these? Okay, so good job on those. If anybody else still needs one of those, I got a few extras up here. Start working on those. Okay, you got a couple weeks till outline and notes, so I can't remind you. Make yourself a reminder. Schedule an hour or two every week to work on that, and you'll be in good shape. Number 81. Alkaline battery. These are your Duracells. Caden, what are you working on?
I was writing some down my phone. So
Good boy. Okay, this is literally what happens inside of your batteries. Okay, the shell, the metal casing on a battery is zinc, and inside is manganese dioxide, or what we call manganese 4 oxide. It is a paste, so there's a little bit of water in here. Look, I skipped the water again, but there is some in there. And again, we're going to ignore the water in this one. Don't always ignore the water, but in this case, it doesn't mention the water, doesn't give us any quantity of water. We're going to skip. Well, water is important in batteries because ions don't travel without some kind of a liquid medium. Okay? And then Mn2O3, this is manganese 3 oxide. Did they balance it for us? It looks like it. They got a 2 here, and that's it. Letter A, determine the limiting reactant if 25 grams of zinc, write it right underneath your reaction, react with 30 grams of MnO2. 30.0, sorry about that, 30.0, 25.0. Letter B, determine the mass of zinc hydroxide, question mark over here, in grams are produced. Okay? Now we're going to follow the same steps, but I need to do something before I can start doing what I just did with you. What do I need to do first? Change everything to moles, okay? So everything in chemistry from now forward, it happens in moles. So, 25 grams. Change the zinc into moles. 30 grams. Change the MnO2 into moles. Okay, zinc is easy. Just read it off the periodic table, 65.4. MnO2 is 2 times 16 plus manganese, which is 55, 65, 75, 85, 87. Okay, so just figure out your molar masses. You should be able to do them very fast. If you get stuck on a molar mass, oh my soul, it'll take you an hour to do one of these, okay? Keep working, keep practicing. Get your calculator out, figure out what these two numbers are. If I remember correctly from this morning, the second one is 0.345. That one's easy to remember. And the first one was 0.3 something or 3 what? 382. I'll take Connor's word for that. 382 moles of Zn. Okay, so now we're going to take these two numbers and we're going to do the same thing we did before. We're going to take the ratio of what I'm given and the ratio of what I need. Okay? The given ones are these two numbers. So I can take this divided by this or this divided by this. Again, I like numbers bigger than 1, so I will divide the bigger one by the smaller one. But again, you don't have to. So it's going to be 0.382 moles of zinc divided by 0.345 moles of MnO2. I'm going to scroll this up and shrink it a little bit so we can get more on the board here. This is what I have, HAV. In the habit of labeling these two things so you can compare them and not lose track of them. What do I need? That's going to be the coefficients from the balanced chemical reaction. Is it 2 to 1 or 1 to 2? Or 1 to 1? What's the coefficient for the zinc? What's the coefficient, MnO2? Okay, so it's 1 and 2? Right? Yes, no? Everybody double check. 1 to 2, right?
There's no.
Number 81.
1 to 2? Okay. Okay, take your calculator, divide these two numbers. And we're going to get 382 divided by 345 is 1 point something. No way I can do that in my head, so clear 0.382 divided by 0.345. 1.107.
What'd you divide on that again?
Question?
That step you just did.
This divided by this. I take the two numbers that I got for the moles, with the two reactants, and take the ratio.
I'm just trying to simplify it down so you have one in the bottom.
Yeah, get the one in the denominator, otherwise you can't compare numbers that don't have the same denominator. Okay? Over here, 1 divided by 2 is 0.5. Change it into a decimal and put it over 1, just so you can see that you have exactly the same denominator, exactly the same thing. Okay? So then, thinking caps on. Which of these numbers? This is what I have. This is what I need. I need to have 0.5. I have 1.107. Ask yourself that question. Do I have enough of this to meet this need?
Yes.
Yeah, I got twice as much. So that's going to be excess. And that one down in the bottom will be the limiting reactant. Okay. Go back to your reaction. Label them LR and XS. So zinc, plenty of it. Cross out that 25. Limiting reactant, MnO2. We're going to use 30 grams to do our stoichiometry problem. Sounds like a lot of work. It is. Okay. But now we figured out what is limiting this reaction. So I'm going to take the 30 grams of MnO2, figure out how much of this produces. This just goes back to what we've been doing the last 3 days. And we're just going to crunch it. So start with 30 grams. Now this time we're going grams to grams. So remember, I got step 1 to 2, step 2 to 3, step 3 to 4. 3 conversion factors. Everybody say it with me. Molar mass, mole ratio, molar mass. Molar mass, mole ratio, molar mass. Okay, it's always in that order if you have the 3-step problem. Okay? You got to change this into moles first. Now, watch. Do I need to do it again? I already calculated it up here. So here's the molar mass of MnO2, 87. Cool. Save some time. 87 grams down here. In 1 mole of MnO2. Then in the middle, mole ratio. Go back to your reaction. Remember, now we're talking about a product. So we haven't even talked about this yet, but it's got a coefficient of 1 to 2. So 1 for the ZNOH. And that goes in the numerator. We're going to produce 1 mole of ZNOH2 for every 2 moles of MnO2, that are used up. And then the third step, change the ZNOH2 back into grams. We need the molar mass of zinc plus 2 hydrogens plus 2 oxygens. And that'll give us grams. ZNOH2 per 1 mole of ZNOH2. Okay? 16, 32, 34, 90, yeah, that sounds right. 99. So 99 grams for ZNOH2. Calculator 30, now check your units. Always check your units. Grams of MnO2, grams of MnO2, good. Moles of MnO2, moles of MnO2, good. Moles of ZNOH, moles of ZNOH, good. Again, if you constantly review those, you can't go wrong. The numbers will be in the right position. 30 times 99 divided by 87 divided by 2. How much?
17.1.
17.1, sounds like the right number, and that units will be in whoops, 17.1, in grams of CN, parentheses, OH, parentheses, 2. Okay. Questions?